Hello everyone, this is University of Ottawa's group for solid waste design competition. Our presentation is about cost-benefit analysis of using source-separated organic material in a composting versus landfilling. For our overview, I should notice that according to recent statistics, global waste production has increased by over 50% in the last 3 decades, and over 2 billion tons of municipal solid waste is produced annually. Global waste generation is expected to increase by 70% in 2050, with 3.4 billion tons of solid waste generated. Improper disposal of waste can lead to severe environmental and health impacts, and the biggest global concern is sustainable and environmentally friendly waste management. Composting and landfill gas collection are two of the effective methods in managing organic solid waste. What is the composting? Composting converts organic waste into nutrient-rich compost through biological decomposition. By composting, it reduces the volume of organic waste in landfills and reduces methane emissions by diverting organic waste from landfills. Landfill gas collection. It collects methane produced from the decomposition of organics in landfill and converts it into renewable energy. Landfill gas can be used to generate electricity, heat, and fuel for vehicles. Our objectives through this presentation are conduct a cost-benefit analysis of two waste management scenarios, landfill RNG and organic composting. Compare between these two scenarios for a collection, transportation, treatment, and disposal. And we also investigate the environmental performance, energy recovery, potential, and land requirements of both scenarios. Here is our both scenarios with the mentioned population. In the first scenario, shown below here, as you see in the picture, involves collection and commingled waste, transportation to bioreactor landfill, collection of gas, and on-site conversion into RNG. And as you see in the second scenario, we have two ways, and some of the waste are going just to landfill. The second scenario shown below involves separation of organics at source, processing organics at composting facility, landfilling the remaining waste, and marketing the compost. And our waste collection and transportation in this section, we compared the both scenarios for the collection and to transport the waste through the landfill or composting. And the collection of landfill RNG system and the organic composting system was designed and compared in here. Specific weight of municipal solid waste, the population, household size, waste generation rate, and organic waste fraction are important factors for this comparison. And the table below provides a summary of the design parameters for the collection systems of both scenarios for the solid waste management systems.
Okay, so moving to the next part, which is the cost benefit analysis. So a financial assessment was conducted for both scenarios, for landfilling organic waste and for composting the organic waste. In order to conduct a thorough assessment, a set of cost and revenue streams must be identified for each facility. So there is two types of expenditures. We have capital investment costs, that is known also as CapEx, and operation maintenance costs, that is known as OpEx. So for the CapEx, it includes the costs required to build the facilities, also for the infrastructure, land, permits, and other capital costs. For the operation and maintenance costs, the operational costs include the utility bills, salaries, supplies, administration, and other indirect overhead costs. And the maintenance costs include repairing, replacing, refurbishing the equipment. Also for the revenues, the key source of income arising from landfill with gas recovery is the electricity. So the energy generated from landfill gas um, is converted to electricity, then it can be sold to consumers. And also the tipping fees charged when collecting the waste or at each facility is also considered a revenue stream. Also, the compost resulted from the composting facility can be sold at market, and it is also a revenue stream. Okay, so the revenues associated with electricity generation from landfill with gas recovery system can be calculated using those equations. So ERP is the energy recovery potential in kilowatt hour. So we can calculate the energy recovery potential by multiplying the total amount of methane generated uh, by the energy content of methane and multiplied by the conversion efficiency. Then the revenues can be found through multiplying the electricity tariff of the country or of the specific location by the amount of energy recovered. So for our case, we took the electricity tariff of US. We used the electricity tariff of US to calculate the energy revenues. Then we have the tipping fees, the revenues from the tipping fees. It can be calculated by multiplying the weight of waste received at the facility times the tipping fees per ton of the processed waste at this specific facility. Then the revenues arising from composting depends on the market price of compost. So it can be calculated using this equation, which is a multiplication of the weight of compost times the market price per unit of mass of compost. Then net present value was used to calculate and assess the scenarios, the examined scenarios. So it represents the balance of all cash inflows and outflows throughout the assessment period. In our case, it's 40 years. So a positive net present value represents a profitable project. So this equation was used, so it's cash inflow minus the cash outflow multiplied by 1 plus the discount rate. In our case, we used the discount rate of United States to the power of minus the time. Then we have assessed the payback periods of each project. So it's a powerful indicator to compare the financial feasibility of the project, and it can be found through it can be found through plotting a graph between the cumulative net present value along the entire period of assessment. The intersection point between the plotted curve and the zero cumulative net present value represents the payback period. Moving to the environmental assessment, as greenhouse gas emissions has been a global concern due to climate change, global warming, and other major impacts. We calculated the environmental impacts of the studied scenarios. So carbon dioxide emissions from the decomposition of organic waste is considered as a part of the existing carbon cycle, and thus it's negligible. So we calculated the methane emissions from each scenario as it has a higher global warming potential than carbon dioxide by 28 to 36 times. So for composting, okay, so the methane gas released during composting can be estimated using this equation from the tier 1 of IPCC. So the total emissions in a year equals to the mass of organics treated that year times the emission factors, and then subtracted by the amount of recovered methane in composting, as we don't have um, any methane recovered, so it's zero. The table shows what does each parameter stands for and the default values suggested by IPCC. Then for the landfill gas, the environmental emissions or the amount of methane released is calculated as follows. So using this equation, and also this table shows the parameters, what they stand for, and the default values by IPCC. So basically it's the total amount of methane generated minus the recovered methane, the amount of methane recovered during the gas collection process. Then we calculated the energy recovery potential, as it's an important parameter because the energy recovered from landfill gas can substitute the fossil fuel used to meet the energy requirements. So landfill with gas recovery can convert the energy content of organic fractions into energy. The energy recovery potential of landfill gas was calculated using this equation shown in the slide. So it's basically a multiplication of the amount of methane produced times the energy content of the methane times the conversion efficiency. Okay, so the last parameter used to assess the examined scenarios is land requirements. So the land required to carry out each scenario was calculated. In case of landfill, several parameters are needed to calculate the land requirements, such as waste settlement, compacted density, waste to soil ratio, height above and below ground, slope above and below ground, auxiliary factors to account for the administration building, let's say, and the additional facilities around the landfill. So all these values were retrieved from literature. For composting, the land requirements was calculated by multiplying the amount of waste times the land required per mass, per a unit of mass of waste composted. Then the land requirements were compared between these scenarios.
As it was presented earlier, the collection system for both scenarios was designed. The landfill RNG scenario generates almost 1,000 tons of waste per day and requires 10,000 containers for landfilled waste. The collection frequency for both landfilled and organic waste was assumed to be 3 times a week, and the truck volume size for waste collection is 100 cubic meter. The container size for the organic waste ranges between 3 to 4.5 cubic meters, and the truck volume size for the waste collection ranges between 32 to 55 cubic meters. Based on the calculations for the collection and transportation, it was found that the organics composting scenario had overall more advantages. That is due to its potential in reducing the amount of waste sent to landfill, as well as increasing compost production and potentially decrease greenhouse gas emissions, as will be elaborated later on. Now I'm going to be discussing the results of the environmental assessment and land requirements. So the findings of the environmental assessment were based on greenhouse gas emission calculations, which were mostly in favor to the composting scenario. The results indicate that the OCS scenario had lower GHG emissions compared to the LRS, with 500,000 megagrams of CO2 compared to almost 900,000 megagrams of CO2 for the LRS. Now, this significant difference between those two scenarios was mainly due to the fact that the landfill RNG involves the generation of methane from landfills, which is a potent greenhouse gas, whereas the organic composting scenario diverts the organics from landfills to a composting facility, hence it reduces the total methane emissions. Now, in terms of land requirements, the landfilled RNG scenario had a projected land requirement of approximately 1 million square meters in 2065, which is considerably lower than the organic composting scenario that requires almost 3.5 million square meters. The landfill RNG scenario involves transporting all waste to the landfill, which requires a relatively small land area for the landfill and transfer station. On the other hand, the organic composting scenario requires much more land, as it needs 2 transfer stations, one for the organics and the other for the landfill waste, in addition to a bioreactor landfill and a composting facility. The results of the net present value analysis show that the LRS scenario had a net loss and that the system would start losing money by the year 2032. This indicates that the LRS system is not economically viable in the long term. In contrast, the OCS scenario showed a payback period of the year 2031 and a cumulative net present value of 19 billion USD, indicating that the system is economically feasible in the long term. Now, the landfill RNG scenario shows a negative net present value, indicating a net loss and a shorter payback period, which confirms that the system is not profitable in the long term. In contrast, the organic composting scenario shows a positive net present value, indicating profitability and longer payback period, which suggests that this system provides a better long-term investment. Now, this analysis reinforces the importance of considering economic factors in waste management decision-making. Now, in addition to the previous assessments, a sensitivity analysis was performed to assess the robustness of the results and to identify the most important factors that affect the economic and environmental performance of the two scenarios. In this analysis, the parameters involved in this financial analysis, as well as the calculations of land requirements, energy requirements, and greenhouse gas emissions, they were all varied by plus minus 20%. Now, the financial analysis showed that the first scenario was more sensitive to changes of the RNG plant and transfer station and the operating and maintenance costs, while the second scenario was more sensitive to changes in compost price and the O&M of the transfer station. Moreover, the land requirement calculations showed that both scenarios were sensitive to changes in waste generation rates, with the second scenario being more sensitive due to the need for separate organics collection. In terms of the greenhouse gas emission calculations, it showed that the second scenario had lower sensitivity to changes in transportation emissions, as separate organic collection reduced the need for transportation of organic waste to the landfill. Overall, the sensitivity analysis results suggest that the second scenario may have more variables to consider. However, it results in greater environmental benefits and potential revenue streams. Now I'm going to be giving an overall summary of the conducted analyses amongst the system. So the net present value of the LRS was 1.5 billion USD, while that of the OCS is higher at 2.7 billion USD. The landfill RNG scenario generated almost 87 billion megawatt hour of energy, while the OCS did not generate any energy. The land requirements for the LRS were 1 billion square meters compared to almost triple that of 3.4 billion square meters for the OCS. Now, the LRS produced almost 900 million megawatt grams of CO2 in greenhouse gas emissions, while the OCS produced significantly less at 500,000 megagram CO2. Now, these results indicate that the OCS is more financially viable and environmentally sustainable option compared to the LRS system. In conclusion, the organic composting scenario appears to be a more sustainable and economically viable option for waste management in this location. The OCS system has a shorter payback period, higher net present value, and significantly lower greenhouse gas emission. The higher initial investment required for the OCS system can be justified by the economic benefits and environmental impact reduction. Now, additionally, the implementation of a comprehensive life cycle cost analysis and life cycle assessment, as well as eco-efficiency analysis, should be conducted for the OCS system to ensure its sustainability in the long term. These are our references, and thank you.